Hello again, ECON1005 students. The presentation today will be looking on Unit 7, Estimation. Now, estimation uses sample data to calculate a single value or a range of values that serves as an estimate for an unknown population parameter. Now, the point estimate is a single number, while interval estimates, which we commonly refer to as confidence intervals, would be a range of numbers. Now, let us suppose that our population mean, mu, is unknown. Then we will use a sample mean as an estimator for the population mean. Similarly, we can use the sample median, the sample mode, or the sample trimmed mean as estimators of the population mean mu. The sample variance is an estimator for the population variance, and the sample proportion is an estimator of or for the population proportion. Now, let's look on this past paper question. It's from May 2007. The verbal and math scores for a random sample of 200 students sitting the SEA exam in 2006 were collected and analyzed and shown in the Minitab output below. So here you see there are scores for verbal and for math. You can see there are 200 students sitting the verbal exam, 200 sitting the math. You can see the mean scores, standard error mean, trimmed mean, etc. Now the question states, assuming normality for both the verbal and the maths scores, state clearly the estimators and estimates of the parameters of these distributions. Now the estimators, that would be the sample mean, sample median, and the sample trimmed mean. And the estimates would be the actual values, right? So if I go back to the question, it wanted us to find the verbal and math scores, estimators, and estimates for the parameters. For normal distribution, the parameters would be the mean and the standard deviation. So for both the verbal and math scores, the estimators for the mean would be the sample mean, sample median, and sample trimmed mean. For both of the verbal and the math scores, the estimator for the standard deviation will be the sample standard deviation. Now the estimates for the mean verbal scores, the estimates now would be the actual value. So the mean estimate would be 595.65. The median estimate would be 586, and the mode as an estimate would be 595.57. Rather, not the mode isn't here. The trimmed mean would be 595.57. The estimates for the math mean, similarly, we'll read that from the table. And the estimates for the standard deviation, verbal and math scores are given here, 73.21 and 66.33. So when I ask for estimators, I'm asking, you should think of words. So the estimator for the population mean will be sample mean or sample median or sample mode or sample trimmed mean. And the estimate would be the actual figure. Now, let us suppose that we have a population of 5 students. These students are student A, B, C, D, and E, and their marks for history tests are shown below. So student A got 70, student B got 78, etc. When we find the mean score was 80.6, and the population standard deviation was 8.09. Now, assume that this population value is unknown, and we are going to estimate, and we want to use the sample mean statistic as the estimator. What we're going to do here is to take a sample of size, let's say 3. We're using 3 for this example. So from this population of 5 students, you can get a possible 10 random samples. There are 10 ways in which you can choose these 5 students. And I have a list here of the 10 ways in which you can choose the 5 students, and the scores of these 5 students in each of these cases, and the sample mean for each of these cases. So if I chose student ABC, the scores would be 70, 78, and 80, and the mean would be 76. So I end up here with 10 sample mean scores, right? Now, if I find the mean of these means, my answer would be 80.6. Now, if you recall, when we had the actual 5 figures, that is all the items in the population mean was 80.6. And now when we take all the possible samples from the population and we find the mean of these sample means, we're getting the same 80.6. So here, the mean of all the possible sample means equals the population mean, right? This implies, therefore, that the expected value of the sample mean equals the population mean, right? And this is a fact where we say, this is where we say that the expected value of the sample mean is equal to mu. Therefore, it makes the sample mean the unbiased estimator for the population mean, right? Because the expected value of the sample mean is equal to mu, it means, therefore, that the sample mean is the unbiased estimator for the population mean. Now, sampling distribution of the mean. Now, so remember, we have all these sample mean values. So we're looking on the population distribution of these sample means. Okay? Now, so that's here. I have X bar, because it's the sample means. It's normally distributed. The mean would be mu, just as it would be for the population. But the key thing to note here is that the standard deviation would be equal to sigma, that is the population mean, divided by the square root of n. Right? This value, standard deviation over the square root of n, is known as the standard error of the mean, SE mean. You would have seen that on the Minitab output I showed you earlier. SE mean is the standard deviation of the sample mean. Now let's look on this question. It's a final exam question from December 2010. The population mean cost of a textbook is US $92. A random sample of 35 textbooks is selected from this population. What is the probability that the mean cost of the sample is less than US $80? Now this is a sample mean. Notice the variable is a sample mean. Right? What is the probability that the mean cost of the sample? Okay, so our variable of interest is the sample mean cost of the textbooks. Okay, mu is equal to 92. N is equal to 35. The standard deviation is 5. We want to find the distribution before I get to what we want to find. The distribution, X bar, is normally distributed. Mu would be 92. And the standard deviation would be, or the standard error mean would be 5 over the square root of 35. That is the standard deviation of the sample mean distribution. Probability that X bar is less than 80. Then we're going to standardize 80 minus the 92 over 5 divided by the square root of 32. We find out what that value is, and we'll go to our normal distribution table. Right? So this is a little different than just the normal distribution question. This one is a sampling distribution. All right, so it's the distribution of the sample mean. So you'll see that keyword sample. What is the probability that the sample mean? Okay, that's the keywords to look for in a question like that. We're going to move on quickly to confidence interval. Now here, instead of just a value, a point estimate, we're looking for interval estimate a range of values. Now this is the formula. Looks a little complicated at first, but when we look at it, you will realize it's not as complicated as it looks. 100 minus alpha, that indicates the percentage of confidence that we're looking for. So let's suppose it's a 90% confidence interval. It's equal to x bar, that's your sample mean. Z alpha over 2, that's a critical value we're going to find from the tables. Standard deviation over the square root of n. Now, before the comma here, what you have is a lower bound, and then after the comma on the right-hand side, you have the upper bound. So it's a range, right? So the lower value on my left, the upper value on my, or the higher value on my right. Now, let's suppose we're looking for the 95% confidence interval. So if I draw my normal distribution, you will see it here. I have 95% distributed in the middle. All right, my mu would be right in the center there. You know, the mean, the normal distribution is symmetrical about the mean. Okay, so the mu is right there in the middle. Now, if I have 95% confidence, the total area under my graph is 100, so I have an extra 5% that has to share on either sides. So here I'll have 2.5%, there I'll have 2.5%. Right, so that's where this 0.05, so that would be that 5% dividing by 2 for the two tails. Right, so I'll have Z 0.025. And I'm going to go to the normal distribution tables, and I'm going to look in the body of the tables where the probability values are for 0.025 to find the corresponding Z value. Okay, when you go to the tables, that corresponding Z value would be 1.96. All right, so now we know for 95% confidence, it will be the sample mean plus or minus 1.96. Now for another level of confidence, this critical value will change. It won't be 1.96, it will be some other value. For 95%, it is 1.96. For another confidence, then it will change. If you look on this question has to do with 97% confidence, right? So a random sample of 100 students who visited a department store spent an average of $77 at the store with a standard deviation of $19. Calculate the 97% confidence interval for the population mean. All right, so 97% confidence, it's x bar plus or minus. Now it's 97%, so we're leaving 3% to share for the tails. 3% divided by 2 is 1.5%, so that's 0.015, right? Standard deviation over the square root of n. Now, when you go to the tables and you look in the body of the tables, the normal distribution tables, that's table 3 in the course manual, it will correspond to a Z value of 2.17. So here you'll see that 97% confidence corresponds to a critical value of 2.17. All right, so now we can substitute our values. The sample mean from the question before was 77. The standard deviation was 19, and our sample size was 100. So we plug those values in. Our lower value works out to be 72.88, and the upper value works out to be 81.12. All right, we can write it as an interval. Mu lies between 72.88 and 81.12. Here is a past paper question. I didn't make a note as to what year, but you were required, the students were required at the time to calculate the 93% confidence interval for level 3 and to interpret the results. Okay, so 93% confidence interval. You would have 7% left to share for both tails. So each tail will be 3.5%. So that's where the 0.035 comes from. You will go to the table, in the body of the tables where the probability values are, to find the corresponding Z value, and it would be 1.81. The mean values are given in the exhibit, and the standard deviation is also given in the exhibit, and the size n is given in the exhibit. Plug those values in. Now the interpretation. In the exam, the interpretation is worth 3 marks, so you have to pay careful attention to this interpretation. And how do you interpret the answer here. If large numbers of samples, each of size 202, because that was the size of the sample for this question, are drawn from the population, and the sample mean is calculated, then 93% of the time, the sample mean computed will lie between 22.357 and 23.287. All right, here for 98% confidence, I'm saying here, find what that z-score would be, and your answer should be 2.33. What if our sample size was small? If our sample size was small and we don't know sigma, population standard deviation, we will have to use the t tables to find that critical value, that t-score right there. Notice the formula looks more or less the same. X bar minus, instead of z though, we have a t, and instead of sigma, we have s. Right? If we're using the t-tables, we need to use the degrees of freedom, and the degrees of freedom for the t-test is n minus 1, your sample size minus 1. So here's a question. 14 ECON1005 students are randomly selected and their ages were noted. The information was inputted into Minitab and the display below was generated. So you'll see age, 14 students, the mean, the standard deviation, the standard error mean, 95% confidence. Now the lower bound is 24.73 and the upper bound was deleted. You were asked to find the upper bound. Okay. Now, if it's a 95%, you know that you're going to have 2.5% on either tails. You're going to go to the normal distribution table. The degrees of freedom would be 13 because n is 14. So 14 minus 1 is 13. You look for degrees of freedom is 13. And the 0.025 and the t-score would be 2.16. So you're going to be using 2.16 for your t-score. The mean, sample mean is given in the question, the standard deviation, sample standard deviation, n, etc. You plug those in, right? The upper bound, you can see, worked out to be 24.73. The lower bound was 24.73. The upper bound was 35.99. You may also be asked to find the confidence interval for the population proportion. This is what the formula looks like. This is for a large sample. So here we have surveys carried out in a city, 170 households out of a random sample of 250 owned at least one pet. You need to find a 95% confidence interval. Now 95%, we know already how to find that z-score right here of 1.96. This P with a line under it, that's your sample proportion. And your sample proportion is 170 out of 250. So that's P. And you know P and Q should add up to 1. So if P is 170 over 250, then Q would be 80 over 250. So you plug those values in, simplify, and solve. And this would be your confidence interval for the proportion. This brings us to the end of the presentation on Unit 7. I hope you found it helpful.